send you the link later on, no problem. Okay, so 8 sessions in total, and each time we can spend around 3 hours together, and we are going to cover a number of different aspects. So that's the first thing I wanted to tell you. The idea how we can organize the time is that each day, maybe today is a bit different, but not too much, we spend around 1 hour 45 minutes to 2 hours of lecture, and there is a short break, let's say in the middle after 1 hour. Then we take a 10-minute break, and then we have some time for your questions, and I'll try my best to provide answers, of course. We can discuss things, and then I have a range of activities to share with you. So that is not only me lecturing all the time, but you also get to practice a number of things. So that's usually how I work with my students here at the university. We have time for activities. Of course, we're online, right? So it's not as good as if we would be face-to-face, but there is no way for Hong Kong residents to travel easily these days. So it's online, and let's see in the future what happens. But that's how we can organize the time together. All the lectures, the slides, the recorded presentations, maybe I can put the links there as well. And other things I will put on Google Drive. And here you have the link. And this link, if you visit the page, then you'll find the slides, mostly the slides and other documents. So I have already uploaded what you see right now, and the first lecture is uploaded. And then every day I will upload more until the last session. Let me see if I can copy this easily. I will try to copy the link here so that you have it in the chat, so you can keep this one for the coming days. And if I just tell you a little bit more about myself, who I am. So I'm an assistant professor, so at the University of Hong Kong. I came here in September 2018, so that's 3 years and a half ago. And before that, actually, I worked in France, and I'm not sure whether you have heard of it or not, but the main research institution in French, which is the CNRS, the National. So I hear some people in the background. Maybe just mute yourself for now. I will try to mute if I hear some noise. All right, okay, it's gone. Otherwise, that will make it a little bit more difficult. So yeah, I work at the French CNRS for a number of years. And although I'm in linguistics, and I'm in the Department of Linguistics here at HKU, basically my educational background is in computer science and cognitive science, which is broadly the study of the human mind. And my research is on language evolution and complexity. And what I do most of my time is basically I apply data science techniques to the humanities and social sciences, different questions about language and languages or literature, or the analysis of news articles on different topics, and so on and so on. If you need to send me an email, if you have questions or stuff, I will try to address them. You can see my email, and actually you have received my email from yesterday already, so you know this already. So that's how you can contact me outside of the time we will spend together. So am I right to say, maybe you can let me know, am I right to say that most of you, or all of you actually, you know data science to some good extent, but natural language processing is something you haven't covered in the past? Am I right to say that? You can let me know your answer in the chat, or you can turn on your mic, just that I confirm what my hypothesis. Is natural language processing something completely new, or have you heard of it before? Do you have some expertise actually already, or what would you say about yourself?
Yeah, on my side, what I can say, for me, it is almost like my first time
Okay, good. Okay, new to you. All right. So don't worry. Usually that's, I mean, I'm going to share with you some course content that I usually teach my students in the Faculty of Arts, which means that, oh, okay, someone is using it. Okay, Janvier, you are using it in your research. Okay, so I'm not going to assume you know much at all about NLP. So some of you, if you are using it, then maybe it's going to sound very familiar. Maybe it will sound a bit too easy. I hope that won't be the case. If you're new to it, normally, I mean, I will move gradually and I will cover a number of topics and you should be able to follow. That's the point, is not to lose you, of course. Okay. All right. So let me just briefly introduce the course, the time we can spend together. Natural language processing, very broadly speaking, it's a field which addresses how, let's say, computers, machines analyze, produce, and understand natural language. That is our system of communication. And when we say language, that's broadly speaking. Of course, most resources concerns English, but natural language processing has to do with all the languages spoken by human communities on our planet. And of course, that includes Asian languages, Indo-European languages, languages spoken in Africa, in South America, and so on and so on. For some languages, we have more resources, and for many other languages, then the resources are way more limited. Of course, I'm going to focus mostly on English, but I hope that you will keep in mind that what you can do in English, theoretically, at least you could do it with any other language. And for some other language, like French and German and Dutch and Arabic and Chinese, you have actually a lot of resources available. Now, if you speak a language, let's say from an African country, which do not have a lot of speakers and do not have a lot of recordings or text, then of course, it's harder to create systems which require this text and materials for training to create a system that works well. But that's just the way it is, at least today. So this field, natural language processing, it's in between, let's say, linguistics and computer science, and it covers a wide range of techniques. It has to do with automatic speech recognition, text mining, machine translation, or yet speech synthesis. How you can have computers which create sound and can speak the way we speak. So in this course, we are going to introduce NLP, broadly speaking, but we will focus more specifically on methods and challenges of text mining. Because very likely, if NLP could be of interest to you, given what you are doing, given your research projects, given your the courses you study, and so on, I guess text mining is the area where it's, I mean, you can more readily apply the tools and the ideas and the methods. Speech synthesis is something way more specific, so I will not really cover that. Natural language processing actually is not something that was discovered like 10 years ago. It's actually an old, with quotes, subfield of linguistics. So like several decades of existence. People, they were already trying to synthesize speech like in the 1950s, for instance. But this being said, in the last years, the field has changed a lot. Or you could say it has been revolutionized because mostly with the development of deep learning. And today you have a very strong research drive by a number of big companies that I'm sure you know all very well, like Google, Facebook, Tencent in China, Microsoft, etc., etc. They have a lot of very good, talented researchers, and they have a lot of money, which means they have very strong computational resources. So they can do things that everyday people with their everyday computer cannot do, or even in universities is hard to compete with them because they have really the manpower and they have the resources and everything. And it's a field which moves very, very fast. So if you go to a conference, you could hear that the oldest paper that people mention is only, let's say, 3 years old or something like that. So it's super, super fast. And as it makes progress, the performances, they are gradually getting closer to human abilities. It's not perfect yet, far from it, but really it becomes more and more impressive. And I will show you some examples of that. What I will do in this seminar, I will try to cover both the more classical approaches before deep learning, but then I will also tell you a little bit about deep learning and how you can apply it to natural language processing. I'm not sure how familiar you are with deep learning. I guess some of you are doing at least a bit of it. And I guess some of you have not yet come into contact with deep learning. Am I right to say that? Are some of you like pretty good at deep learning? And are some of you like rather new to deep learning? Can you let me know, like typing in the chat? How are you with deep learning in general? Are you using some of the methods?
Yeah, most of the first time.
Okay. Okay, so you have some background in deep learning. That's good. Use some methods. Okay, some networks, I guess. Not an expert. Okay, I'm not a definite expert in deep learning myself, but I'm using it for a number of tasks. So I know it well enough that I can share a number of things with you. But I expect that some of you will know it quite well, and maybe, yeah, most of you, maybe you are quite familiar with it. Then, of course, it will be easier. All right. Two different questions when it comes to processing natural language with computers. What and how you do it. So what can you do and how can you do it? So we will focus on both elements. I will try to convince you that natural language processing and text mining is something interesting and what scholars and engineers they are doing in this field. And then I will try to also show you some concrete techniques. I will try to share with you some basic skills when we have the activities together. So for instance, if you have never done a regular expressions, that's something we will do together. Or we will try text generation also. We will try a number of things and have some resources to share with you in the coming days. So hopefully when we finish together next Wednesday, you'll be able, that's what we call the course learning outcomes here at the university. They like this very much. So you'll be able to describe some key aspects of natural language processing. You will be able to articulate like the techniques, the achievements, and the challenges of text mining. And then you'll be able to apply various text mining tools to a text corpus, and using some software I will share with you. So that's what I have in store. And hopefully that's something you'll find interesting once again. So slightly more in details for the course content. Today, I will introduce NLP, broadly speaking, and a little bit of deep learning. Tomorrow, I won't focus on text for one session, but I'll tell you a little bit more about speech recognition. So how you can recognize speech, the sounds of human speech. And then we'll focus more on the written aspects. I'll tell you about autocorrection, spell checkers, and how you can go beyond that. Then we'll see how to process what we call in linguistics morphology and syntax. So the shape of words and how we put words together in sentences. I'll tell you about text curation, then some classical approaches in text analytics, some more modern approaches with deep learning. And finally, I'll show you how you can apply these text analytics to literature, like some things people do in arts, some interesting thing you can do. So that's what we can cover together. And then if you go a little bit in detail, you can see the kind of stuff I will address in the different during the different lectures. If you have, I will tell you a little bit about the word embedding, for instance, in the 7th lecture. During the 6th lecture, I will tell you about topic modeling, sentiment analysis, document term matrices, these kind of things. Morphological processing. Well, you can see it on the slide, but yeah, we are going to cover these different elements together. That's the plan. We'll have a number of activities together, I've told you. So some, they will be, let's say, programming free, but I've been told you are all using R. So I will also share some simple pieces of code written in R so that you can run them on your own computers, and then you can get the results, and then you can start to play with the functions and tools which are commonly used for text mining and which are readily available in R. Yeah, and I see the message. No problem. Yeah, I will share all the slides and I will share the recording. So don't worry, everything will be shared. No problem. So yeah, and I have a number of Shiny. I'm not sure if you have heard of Shiny. Shiny is something you can use in R to create graphical interfaces. And I've created a number of them and they are available online. It's very easy to access them and we can try to use them. The only thing is that if you are like around 50 people and you all try at the same time, I'm not sure the server will cope with that, but we can give it a try and then you can try later. And I mean, they are available online. So I will share them with you and we can use them for some of our activities. So I will also tell you more about that in the coming days. All right, and that's the introduction, what I can share with you for this coming days. Does that sound okay to you? Is it more or less what you have? Does that seem something that will be useful for you? Is it okay? All right, okay. So I'm sure I won't be able to please everybody, but if I can please most of you, then of course, then the contract will be fine. Good. So let's start. Let's start with the first one. What I want to do today is start gently, and I want to introduce natural language processing to share with you some broad ideas, some broad definitions, and then I'll also tell you a little bit about deep learning. And of course, if you know it, that will be very simple, but I will try to introduce a number of aspects and then some activities. So the question I want to address, first, what is natural language processing? What does it cover more precisely? And what are the main issues maybe and the main challenges? And then since questions in natural language processing today, they are more and more and maybe mostly addressed with deep learning now, how do you do this? What is deep learning and how can you apply it to the processing of human language? So that's the two main questions for today. I want just to share an example with you. So hopefully it will play well and you can hear and see. I want to share, just have a look at this video for 30 seconds, and then I'll just tell you a few words about it. So it should play and you should be able to hear it and everything. Okay, so this is a short video of something we won't cover much together, but this is part of natural language processing. This is part of speech synthesis. This is an example of how you can create human sounds, speech sounds, using articulatory speech synthesis. So what you can see here are models of what we call the vocal tract. And you can see that has the different articulators, the vocal folds, the tongue, the jaw, all these pieces, they move together. You can actually hear the result, okay? So that's speech synthesis, really taking advantage of what we know about how we produce speech as human beings. If you use deep learning, you don't have all these articulatory aspects. You do it in a very, very different way. You do it statistically. But this is also stuff linguists in this field will do. They will try to understand how we produce speech and they will try to create models of it. And you could just hear the result. And I'm not sure you could hear what the language was. But if I'm right, that should be Latin. Okay. So this is just an introductory example. So what we will do today at the end of the lecture, you should be able to describe various tasks and issues in NLP. You should be able to relate NLP to some famous ideas which have to do with human cognition, how we use our mind, our brain to process language. You will be able to describe some key concepts of deep learning and how it is applied to NLP. And then I will try to share with you stuff about the statistical nature of language, which is something quite important when it comes to NLP. So that's what we are going to do. First of all, language, linguistics, and machines, something very general. Then I'll tell you more about the different subfields and the different challenges of NLP. Let me see, I hear some background noise and that makes, all right. I will tell you about the different subfields of NLP, then a little bit about cognition, the connections between, let's say, machines and the human mind, then foundations of deep learning, and a little bit more specifically about deep learning and NLP. So that's about the slides that will come in the next minutes and hours. All right. These I share the take-home messages, the key points to take away before I start the lecture, so you know kind of what to expect. I will tell you that the key question is, how can we create algorithms, systems that effectively deal with language? And by language, we mean human natural language. And here there is a question is, can we create such algorithms in a way that they are as efficient as we are as human beings? We are very good at language. So can we really recreate that in machines? And I will tell you that there is a wide range of approaches, of challenges, of achievements. It's quite a broad field, actually, NLP. And I will try to convince you that deep learning is really revolutionary and the results are quite impressive. And the fact that deep learning works so well, I think, is an argument in favor of the idea that the way we process language as human beings is quite statistical in nature. We pay a lot of attention to how words they co-appear together more or less frequently, and we use this knowledge to speak and to communicate with each other. So that's the take-home messages I'm going to basically introduce in the coming slides. So let's start with the broader definition. So the starting point is it goes a little bit beyond natural language processing. The question is, what role can machines play when it comes to language and linguistics? Of course, if you are a linguist, the question will sound a little bit different than if you are not a linguist, okay? But I think it's important not to get confused between different things you can do when it comes to language and machines. So that corresponds to a field that you could call computational linguistics. And I want to emphasize the difference between computational linguistics and NLP. So computational linguistics, that's something, let's say, in between linguistics and computer science. That's kind of very obvious, right? If I give you the name, I mean, that's a very obvious definition. We could say that actually it's the encounter between non-human computers and human language. So there is a human side and there is a non-human, a mechanical, a computational side. And there are a lot of questions actually with respect to what language is and how human beings process language. Because some people would argue that we process language the way, like a computer in a way. That's a very famous metaphor. The idea that our mind, our brain, is kind of a computer, just a computer made of organic materials rather than transistors and stuff like that. So if we don't know yet how to start with this computational linguistics thing, maybe we just look at a couple of definitions. You go on Wikipedia maybe it has changed a little bit today, but I guess not much. You will find that computational linguistics is an interdisciplinary field, okay, concerned with the statistical or rule-based modeling of natural language from a computational perspective, as well as the study of appropriate computational approaches to linguistic questions. So here you see, as well as you have two different things: approaching linguistic questions with computers and modeling natural language. So that's something I want you to keep in mind. And the other very important thing, and I'll come back to it later on, you will see, is statistical or rule-based. And if you do machine learning, I guess you are quite okay with this distinction between using statistics and stuff like what you have in deep learning and using a system with explicit rules. So that's a first distinction that appears in this definition on Wikipedia. Then maybe we go to people who should be more expert than Wikipedia on the topic. So we go and check what you can find on the website of the Association for Computational Linguistics. That's a scholarly institution. They organize conferences on computational linguistics, and they have a journal, I think, etc., etc. And if you check their website, they will tell you that computational linguistics is the scientific study of language from a computational perspective. So from the perspective of how, let's say, a computer works in a way. And it provides computational models of various kinds of linguistic phenomena. These models may be knowledge-based, handcrafted, or data-driven, statistical or empirical. And here you find what we have just heard of before. We heard of rule-based versus statistical. And here this definition tells you of knowledge-based versus data-driven. And data-driven has to do more with statistical approaches, and knowledge-based has more to do with we know what we study, and we are going to use our knowledge to create the computational tool or the computational approach. So once again, this distinction that we should keep in mind for now. Work is in some cases motivated from a scientific perspective, in that one is trying to provide a computational explanation for a particular linguistic or psycholinguistic phenomenon. And in other cases, the motivation may be more purely technological, in that one wants to provide a working component of a speech or natural language system. The way I would rephrase that is when you do computational linguistics, you may feel that you are more of a scholar, of a researcher, or you are more of an engineer. Depends what you want to do. Are you trying to explain something? Are you trying to explain in particular how the human mind or the human brain works when it comes to language? Or are you trying to build a system that will fulfill a given function? If that's the case, then maybe you are more interested in engineering something, and you are not here to try to understand how humans communicate or anything like that. You are interested in building a system. Of course, there are relationships between the two, but there is a divide between these two approaches. It depends what you want to do. Let's say you want to understand how when we hear some sounds tied string together, like apple, we have all these sounds one after the other. It enters in our ears, and then it goes to our brain, and it is processed. And then, in a way, we are kind of looking for these sounds, and we basically pick the fruit. How does the mind do that? How do we go from the sounds to the idea of the fruit itself? Maybe we think that the mind is like a computer, and we try to build a computational explanation, a computational account for how we do that. So that's a specific perspective. It's different from feeling you are an engineer, basically. So you could show it like this. You could say you have different relationships with the machine, with the computer. Maybe your primary goal is to interact with the machine. And rather than using a programming language like C++ or Python or R, you want to use natural language. So you want the machine to understand to some extent natural language. Or maybe your primary goal is different. You want to take advantage of the machine to fulfill another task, especially answer a scientific question, which has to do with language. But the point is not to communicate with the machine using natural language. That's a different thing. If you want to achieve the first goals, the first of the two goals I have mentioned, then you are considering natural language processing. Most of the time, it's more an engineering perspective. Your goal is to build a system which is as efficient as possible. And whether or not it looks like the way humans process language it doesn't really matter. If you can get excellent performances with another approach, perfect. Then you're totally happy. You have done your job. So that's NLP and mostly the engineering perspective. And then it goes in two directions. You can analyze language. Then you have stuff like speech recognition if you are playing with sounds, or text mining if you are playing with text. Or you want the machine to generate language. And then you may have speech synthesis, like the example I've shown you. Or you might have something like automatic text summarization. Let's say you provide a news article to the machine, and you would like your system to come up with 2 or 3 sentences which summarize the content of the article. That's something you can do in text mining. Not so easy, but some people are working on that. So analyze or generate language. That's NLP. Now, if you are interested in the other goal, to fulfill another task, to answer a specific question, most of the time it's a more, let's say, scholarly perspective. Like you want to study a linguistic phenomenon with the help of a computer. Sometimes, but not always, you want to provide an explanation of a linguistic phenomenon on the basis of how a computer can achieve a task. I've told you about reproducing in the computer how we can access words in what we call the mental lexicon, our very own dictionary in our mind, in our brain. But it could be something else. I'm going to give you another example that I was just working on with one of my students this morning. This student is a computational linguist. He is just finishing his MPhil. And for his MPhil, he worked on what we call contact languages. Sometimes in some situations, you have languages which come into contact. So you have people speaking, let's say, 2 or 3 different languages. And when they meet, they cannot understand each other. And then they create a new language. It could be a pidgin, it could be a Creole. And maybe you have heard of pidgins and Creoles, and maybe some of you actually you speak a pidgin or a Creole. It's totally possible. One situation where pidgins and Creoles were created is when African slaves were taken from Africa and brought to the Americas to work in plantations, for instance, and then they met, and usually they spoke different African languages, and then they also met with Europeans. And then the contact between these languages resulted in Creoles and pidgins, depending on the situations, the social conditions. So my student, basically, he has created computational models based on graphs, networks, to study the impact of connecting the people in different ways, the impact on the resulting language. This has nothing to do with NLP. This has to do with trying to understand a linguistic situation with computational models. So, and that's just like, that's an academic, that's a scholarly perspective. So that's what you can do if you are a computational linguist, not doing NLP. But that's actually not the only situation, because you could think of something else. Let's say that you are a professional translator. You translate from Swahili to Kinyarwanda. Why not? Okay. Or from Mandarin to Japanese. Why not? And then to help you. Okay, I mute people when I hear noise, just so that everybody can focus. Sorry for, I'm not trying to being rude, okay? I'm just trying to keep the thing under control. So let's say that you are a professional translator. You could have tools to help you to do your work. Like you enter a word and then you could get different possible translations in the other language, or you could get different synonyms, or yet something else. So here you are not an academic, you are not doing research, but you are using the machine to help you fulfill your task, which has to do with language, your task of translating something. So that's something else, and that's also part of computational linguistics. These days, I'm working with a student to try to create tools to help with creative writing. We're starting to work on that. How you could help when people are writing novels or poetry, stuff like that. Provide them some tools to revise what they write. Try to make it better. Try to craft something more interesting. That's also not an academic question, but that's a tool to help you with something language related. So these are different things. So we are not going to focus much on computational linguistics. That's very interesting, but I don't think it's very useful to most of you, because that's a field of research. It makes more sense to focus on NLP. But what I want you to keep in mind is that it's only one component of what we call computational linguistics. You can do way more things with the machine when it comes to language than pure NLP. So that's something I wanted to emphasize. Are you with me? Is the way I speak, my explanations, is everything easy to follow? Are you okay? Do you have any question right now? How is it for you? That's usually how I teach. Are you fine with that? We're together? Okay.
Yes, we're together.
Okay, very good. So if you have questions, you can write something in the chat, no problem, okay? You can write a question anytime, and since it's on the right side of my screen, I usually spot it quite quickly, and I can try to answer the question. So yeah, don't be shy, of course. Do not hesitate. Just let me know your questions, okay? If I don't know how to answer, I will tell you straight. Okay, I don't know, but I will look for the answer tonight, and I'll come back together. Tomorrow, when we are together, I'll try to come back with the answer. So please don't be shy. Let ask your questions, okay? So I've told you about computational linguistics, broadly speaking. Now I want to convince you that when you do NLP, actually you can do many different things. So that's the second part. You have different subfields of NLP, and each subfield kind of has its own goals. Some of these goals, they are partly shared, but they have their different goals, and the methods are a little bit different. And sometimes you can use the same methods in different areas. You will see that. You will see that what we will use for speech recognition can be used actually for a spell checking to some extent. So there are some connections, but at the same time, there are also different things. So for instance, you have speech recognition. Speech recognition is about having a recording of a voice or someone speaking in a microphone and extracting the words. What is being said? That's one part of NLP, one subfield. And that is different from what we call speaker recognition. Here, you don't want to understand what is being said. you want to answer the question, who is speaking? And there are actually different subtasks here, but you are interested in who is producing the words rather than the content of what is said. Then you have something else. You have language recognition, which means that what you want to know is what language is being used. I'm going to give you a very concrete example of that. Let's say you are in the United States and you have a number of people speaking, you have a number of languages spoken in the US. Or if you think of, let's say, Nigeria, where you have several hundreds of languages spoken by the population. If someone calls the emergency service, the first thing to do is to know what language is being used. It's very hard to have someone who is able, if you have, let's say, 50 different languages, to hear like one or two sentences and know immediately, oh, this is this language or that language. You need to be really, really good to be able to do that. Few people are able, I think, to do that. So can you have a computer that will hear a few sentences and automatically and quickly detect what is the language? And then the message, the call, can be transmitted to someone who can speak, understand this language. That's one example of when language recognition can be useful. Then if you are using Google Translate or other systems like this, then you know of machine translation, right? Translate sentences, texts, words from one language to another. That's a big area. I can share some slides about this with you later on, but we don't have time to cover it, but we could work on that as well. And then you have text analytics. Text mining is when you try to extract the meaning to some extent, as well as you can, the meaning of a number of sentences, of a text, of a news article, of a novel, of a corpus of laws, etc., etc. Here on the right side, you can see someone, and then you can see that he's speaking on the phone or he's speaking on some sort of microphone maybe. And then you can see that you could first start with speech recognition. And then from that, you could move to trying to understand what is being said, accounting for the context of what is being said. Then if you can extract the meaning with this part, then you could have something you have in conversational agents. You could have some sort of dialogue management system. So the idea is to get what the person said, what was the meaning, and try to come up with an answer, maybe using some database containing some sort of knowledge about this or that, depends on the situation. Maybe you can output some graphs, some tables, stuff like that, that the person can see on the computer screen. Or maybe you can generate language and then use speech synthesis so that the person receives, let's say, an answer for a question he or she asked. If you have a system like this, you can see that there are multiple components, and these components, they correspond to different subfields, different questions, different methods. That's all NLP. Some subfields, they focus on text, that's written language, and others, they focus on speech, oral language. Different questions, different approaches, different challenges. On the right side, you can see written language, and here it's handwritten. If you want to create a machine which can analyze something like this, this is a very specific task. That can be very useful. Let's say you write a letter to someone, one of your friends, and you post it, you write the postal code, you write the address manually. You want the post to have today, I mean, that's what post companies mostly do. They use automatic systems to try to automatically decode the address on the letter. And if the system is confident that it can do it well, then nobody will check and it travels, it goes somewhere else. The letter goes away. If the system finds that it's hard to read, then it will signal it, and then it will be processed by a human being with some expertise in this task. Okay, that's NLP. That's processing natural written language. Now on the left side, you see something which is what we call in linguistics a spectrogram. So it's a graph which gives you a frequential analysis of sounds of speech signals. So you speak, and then what you can see, the x-axis is time. The vertical axis is frequency. And then when you see darker spots, darker bands, these correspond to frequencies when you have more energy. And that's how linguists, they analyze speech. They use these representations quite a lot, and we call them spectrograms. So it has to do with acoustics and how we represent sounds. And when you know phonetics very well, you can see that maybe you can see that there are some, you can see some stuff, right? You can see some bands going up, or there are a few things. When you know this very well, you can recognize vowels. And when you see, like, for instance, this kind of vertical bar here, very likely, I would say it's a plosive. So you recognize actually a kind of consonant, something like p, b, g, maybe p, b, yeah, more p, b, where you have some sort of explosion, t, and you can see it on the graph, these kind of things. So it's not exactly the same to process handwritten language, text, and to process sounds. I mean, quite obviously. So these are different subparts of natural language processing. Yeah, sure, John. I will share everything, so don't worry. Everything is already on the Google Drive. Actually, if you were not here at first, you go up in the chat and you will find the address. So all of this is shared. All right. I told you speaker recognition a little bit earlier. Who is speaking? Actually, you have many different questions or many different tasks here. Let's say that you have 5 different possible speakers, and they are all talking to each other. And when you have a voice at some point, you want to identify who is speaking in this closed set of speakers. So you only have 5, let's say, or 10 possibilities, and you want to pick up the right one. That's the first task. Or maybe, let's say that you are working in a place where there should be some access control or something. So you come in front of a door and you say something, and the machine recognizes that it's you, and then the door opens. So that's about verifying a speaker's identity. That's a different task. And here in particular, you are worried that some people, they could try to fake the system and get access when they should not get access. Okay, this is the link to the Google Drive, sorry. All right. Or maybe you have a number of speakers, but you don't know all of them. So you want to identify a speaker, but in an open set of speakers. And as you can guess intuitively, it's harder if you don't know all the possible speakers. It's more difficult than if you know them already. Maybe you cannot identify who it is, but maybe you can identify the age of the person to some extent. Maybe you can identify if it's a woman or a man, or etc., etc. You could try to follow a speaker during a conversation with different people taking turns to speak. I say something, you answer, then I say something, then you answer, and you want the system to track this. So you can follow a speaker, and that goes hand in hand with detecting a change of speaker. Then you could also try to adapt to a speaker. That's when you want, for instance, to speak, and then you want what you say to be turned into text with your computer. Today, the performances are getting very, very good at this task. But before and still today, if you want to get the best performances, what you can do is you can have the system learn some of your features as a speaker, the way you pronounce some sounds, your intonation, the height of your voice, etc., etc. So the machine can adapt to someone in particular to enhance the performances when this person is speaking. And you can work with like individual speakers or with classes of speakers. So maybe you want to verify not only one speaker's identity, but you want to open the door if it is this person or that person, or yet that another person. So you can have classes of people, classes of speaker. So for these different questions, you have different challenges and some techniques which are shared and some techniques which are not shared. I've shown you this already, right? When I showed you the system for dialogue management and everything. Several tasks of NLP, they may be combined in order to tackle a more general task, a more general challenge. Let's consider this app, something like voice translator. So it listens to you, then you say something in one language, and then it will translate it automatically to another language, and it will pronounce it. Then you have different subtasks. You speak. So first, there should be speech recognition. Maybe there could even be language recognition at first. Then, yeah, if the source language is not specified by the user. And then there should be some form of translation and some form of language understanding to do it well. And once the translation is ready, if you want your phone to produce it, to generate it, then you will have speech synthesis. So to create a voice translator like this, you can see the different tasks. Go from speech to text, translate the text, and then go from text to speech. That's how you could do it. Today, you have deep learning systems where you provide speech and it outputs speech, and you don't need to worry about what is in between. That's the more modern take on this question, on this problem. But I'll tell you a little bit more about that later on. It depends, Claude, it depends in which situation you are. Okay, in some situation, you want something to be a closed set. In other situations, open set, actually, if you don't know, you won't be able to identify who is exactly talking, right? Because it's an open set. But maybe what I told you earlier is that you may try to identify whether it's a male or a female, or maybe someone from a specific city, someone from a specific area of a country, this kind of thing. So that's an open set of speakers, and you want to guess something about the speaker, not precisely who he is or she is, but at least some features. Like, let's say you are in France, and people from the north of France, they speak differently from people living and born in the center of France. Maybe you would like the system to pick it up. Why not? Maybe that could be useful. Maybe not. I'm just making the example. So you can verify the identity in different contexts. Depends on your task. You are all doing data science, I think, which means that the way you interact with the machine, most of the time, I think you know how to program. So you are using your programming skills, and that's how you interact with the machine. That's maybe a low level, that's a high level. If you are using R, that's a high level programming language, right? Or maybe you could use a low level assembly language. And that was the case more like, let's say, 30 years ago or 40 years ago. Ultimately, what a computer does, it computes stuff with 0 and 1, zeros and ones. But when you program, you are not programming directly with zeros and ones, right? That's way too difficult. And that's why we have higher level programming language. But ultimately, everything is transformed into 0 and 1s so that the microprocessor can process everything. Okay, that's how we can interact with the machine if we are programmers. If now you are going on Google, maybe, you can interact with the machine with individual words or a sequence of individual words. Okay, I want to know what time it is in Brazil right now. I could type Brazil current time or something like that. It's not a sentence, a proper sentence, just some individual words, and the computer, the system will kind of understand that, and Google or another search engine will return pages where you have hopefully the time that it is currently in Brazil. Maybe a little bit easier yet for people who are not used to interact with machines much, maybe more like older people, for instance, or very young people. Natural written language, that could be a little bit easier. And then natural oral language might be even easier. So maybe we could have what you can see on the slide, that is this arrow representing the ease of interaction with the machine. Zeros and ones, maybe that's the most difficult for us human beings, and the easiest. And then that means that even young children and elderly people, they could interact with the machine, is natural oral language. And that explains, of course, why we want to create systems which can process natural oral language, because then everybody can use these systems and they don't need to know much about computer science and computers. So there is some social impact of natural language processing. That's what I want to tell you with this arrow for ease of accessibility. Creating better connections, better interfaces between humans and machines, that's a big issue in our societies. That having machines which can understand to some extent natural language is very important to interact better with them. That means like we can access maybe information more easily on the internet. Maybe that can make our interactions with computers and algorithms, let's say, faster, more effective. And then it also allows us to interact with objects. If you have some phones, they have Siri. So you just talk to your phone, Siri, can you send an email to Mrs. X to remind her of this or that, or to invite her for this or that, or whatever. Or you can have this on your computer, right? Cortana or these kind of things. So that may smoothen our interactions with machine. But then there is also this issue of democratic access to technology. It's very nice to have very, very fancy computers, but if 20% of the population cannot access them, that's kind of a pity, right? It's not very democratic. So if you want everybody to be able to benefit from these systems, and here I do not mention the possible problems and the ethical issues and stuff like that. But if we see only the benefits, if you want everybody to benefit from the benefits in a way, then natural language is going to be the better way to go. So this is more social, right? Some social aspects of NLP. So NLP can have much impact on our societies, whether in Europe or in Africa or in Asia or yet somewhere else. Some of these consequences, they might not be that positive. It depends on your standpoint. For instance, I'm sure you have heard, and in a way we are all participating in that if we are doing data science, the disappearance of many jobs where machines can do better than us. So today, for instance, you have a lot of companies which will have automatic systems to address their customers' questions. So you go online like a bank, you want to ask your bank something, and then you start to type something, and initially it's a chatbot which answers. It's not a human being. And maybe you will be satisfied with your interaction, and maybe you won't even notice if the chatbot is good enough that you actually interacted with a machine. But then that means no more jobs for people who would have been doing that in the past. It's okay if they find another better job, but maybe not that okay. It depends, right? It's also the constant analysis of everything we do online, with usually a single goal to send us more advertisements and targeted information so that we spend more money, especially buying stuff. Okay? So if you don't pay for something, for a product, remember that it's because you're the product yourself. Your information is sold, and that's the economic model of the business you are interacting with. Your social media messages are treated as well. If you check Twitter's policies, you will see that they can do a lot of different things with your data, with your posts. In some situations, can be very good. Let's say that there is an earthquake somewhere, and people are using social media to send messages to ask for help. If you can analyze this very, very quickly, then you might be able to deliver aid more effectively and more efficiently. But maybe you don't want also your messages to be analyzed for other purposes. If it's about tracking political opponents, let's say, or doing a number of things that maybe are not that sound on an ethical level. So there are pluses and there are minuses in a way. But what you can be sure of is that the rise of AI and NLP, that will transform the way we live. I mean, that's so obvious. So the more beneficial, of course, the better, but there are some drawbacks as well. But more and more, natural language processing is going to have an impact on our societies. And that's even more true today with the development of new language models. The very powerful deep learning models today are so impressive that they are going to take more space in our societies. We will, I think it's fair to say we will see that in the coming years or decades. So we need to be aware of that. That's for sure. Maybe we take a 5-minute break, okay? Just 5 minutes or 3-4 minutes, just that we can breathe a little bit. If you have any question, please write the question in the chat, for instance. And then, 4 or 5 minutes, I will resume, and then we can finish the lecture, and we will have some activities. Okay?
Okay, great.
Okay. So let's just take a short break. I will drink some water so my voice doesn't go extinct.
Prof, we can't hear anything. We can't hear anything. Please check your mic.
Don't worry, I'm not saying anything. So I'm just taking just 2-3 minutes, and you as well before we resume. So don't worry.
All right, thank you, thank you.
No problem. All right, maybe we can resume. Let's move on, and then we'll have another break in 1 hour, and that would be fine like this, I think. Okay, so I hope it's clear enough until now, and then I can continue to move throughout the lecture, and then once again we'll have some activities, and then you'll find everything on the Google Drive online, and the recordings as well a little bit later. Okay, so I have introduced computational linguistics, broadly speaking. I've told you about the different subfields of NLP, the different kind of tasks you may try to address. I want to share with you something more about, let's say, the cognitive background of all of this. Cognitive having to do with cognition, which has to do with the mind and the brain, primarily of human beings, but we could also think of other living species here. So I've mentioned this earlier, is the idea, the computer metaphor of the mind. This is an old idea, actually. This is the idea that, or it's the question whether our brains, our minds, work like computers. Do they process information like a computer does? And of course, since we are interested in language here, in particular when we produce or when we perceive language. And actually, if you are interested in the human mind or in other animals' mind, this is a key question. It's a very fundamental question in cognitive science. And when you do cognitive psychology, it's at the heart of most work being conducted, and especially like psycholinguistics and computational linguistics. And this question is quite old because actually it was born with the first computers. And when computer science started to grow, let's say, started to grow quite some decades ago already now, a number of people gave a positive answer. Yes, our brains, minds work like computers. And that's what we call the computer metaphor of the mind. But actually, people disagree. And more people have disagreed with that. So this is just something I took from a scientific magazine, Psychology Today. And this is what you could read. Recent social and affective neuroscience research shows that a computer is an inadequate and misleading metaphor for the brain. It doesn't work like this. Humans, along with other organisms with brains, differ from computers because they are driven by emotions and motivations. The brain is, in a way, too hot and wet to be represented by a computer. The brain is electrical, but it is also driven by fluids like blood and chemicals, hormones and neurotransmitters. Most importantly, the brain is part of a body which it drives to action. So here the idea is that a computer does not really have a body, although today we have robots and robots have a body to some extent. But the way we rely on emotions and motivations and similar things to speak and to do the things we do would suggest that we are not like computers. But actually, I'm giving you this point of view. Most natural language processing techniques basically ignored such perspectives. But I just want to play a little bit with this idea of the relationship between the brain, the human mind, and computers. So the point here is, if the way we work as human beings cannot be described as computers, is it possible for computers to process language the way as effectively, as efficiently that we process it? If we are that different, can computers reproduce our human performances? That's a very good question. Can we have a computer that communicates as well as a human being? So that's a very important question. And maybe we can push things a little bit further. If you remember the definition I gave you of natural language processing and computational linguistics, a metaphor. Okay, Emmanuel is asking about what is a metaphor. A metaphor is when you basically use one concept to represent another one, drawing some kind of parallel. Let me give you one example. Okay, maybe you know the dove, the white bird, as a symbol of peace, right? This is a well-known symbol of peace. Or a heart, which would represent love, something like that. These are examples of metaphors. So the idea here is that the metaphor of the computer metaphor is the idea that we could represent the mind, the human mind or the human brain as a computer. So there is this kind of connection between two elements. Maybe you could argue that metaphor is not the best term here, but that's how it is called, actually, the computer metaphor of the mind. So I'm just using the term. Does that make sense, Emmanuel? Okay, perfect. Good. So if you remember, I told you earlier that when it comes to computational linguistics, you may consider rules or you may consider more statistical computations. That's what you can do with a computer. So let's now ask the question for ourselves. When we process language, do we have rules in our mind, or do we rather do some kind of statistics? And this is a very important question, and I don't think we have the right answer to it right now, still today. In the 1970s, there was a very famous philosopher, Jerry Fodor, and he put forward what he called the language of thought. And the idea was that, let's say that at the center of our mind, we have a set of rules, something like a grammar, to manipulate symbols. And that's the heart of how the human mind works. So actually, when we perceive something, when we see something, like an apple, the first task of our mind, of our brain, is to transform the electrical signals coming from the eyes, to transform them into the symbol, a representation of an apple, let's say. And then we could use this symbol and other symbols and manipulate them with rules, something like an expert system, very much something like this, to achieve, to do what we do. So we have something like a language of thought. So that's something that was proposed in the 70s. And then the idea is that we process language on the basis of rules, the rules of this internal language. But this is debated, of course. There are other people who have seen language as a set of rules. And whether you speak English or Kinyarwanda or a language from New Guinea. Noam Chomsky, very, very famous linguist, also a very famous political commentator in the US, he wrote quite a long time ago, we are forced to conclude that grammar, the organization, the rules, the organization of language is autonomous and independent of meaning, and that probabilistic models give no insight into the basic problems of syntactic structure. So I need to rephrase that if you are not doing linguistics. For Chomsky, the way we can understand how we can create sentences with words, it's according to a number of rules. And there are no statistics involved. There are no probabilities involved here, only rules. And the idea is that when you are born as a child, you're going to acquire the language or the languages spoken around you. You are going to do this very well, but actually given what they communicate with you, given the inputs you have, according to Chomsky, it is not possible to learn all the rules of the language. So he has this idea, very, very famous idea in linguistics, called the argument of the poverty of the stimulus. The idea that in the stimuli we receive from our caretakers when we are babies, when we are infants, there is not enough to deduce, to infer the rules of the language. So then how can we learn? Then according to Chomsky, it's because we have some innate knowledge of how languages work. We have some rules, some principles that we are born with, that are in our genes. And that's how we can then set up some parameters for the language or languages which are spoken around us and which we are going to learn. If you subscribe to such a view of language, deep learning is not going to work very well. Actually, deep learning works quite well. So maybe this hypothesis, these theories are not that correct. Or maybe the computers are not yet that good. So actually, maybe there are some principles like this. But these are important questions when it comes to language. And we can think of these ideas, these theories, these arguments when we do natural language processing. How can we build rules about language in computer systems? This is one of the interesting questions. Some people will tell you there is no way a machine will ever be as good as a computer. So in 1969, famous linguist John Peirce said, speech recognition is dominated by mad scientists and untrustworthy engineers. Speech recognition will not be possible until the intelligence and linguistic competence of a human speaker can be built into the machine, which is quite obviously something very, very difficult to do. So for this person and other linguists, and still many linguists today, there is no way you can create a machine which can understand language the way we do. Many people have strong feelings about that. They are very convinced by that. Linguists, some linguists at least. But then there are people who disagree. And there is this famous quote by a famous researcher in NLP and information theory, one of the pioneers, Frederick Jelinek. And he wrote, or he said very famously, in my team, every time I fire a linguist, the performance of the speech recognizer goes up. So basically, you don't need linguists to create systems dealing with language. Engineers are enough. Of course, you can imagine that if you are a linguist, you don't really want to hear that, right? But nevertheless, some people have argued in this direction. And then someone commented on Jelinek's approach. Someone commented in 2010, just to celebrate, commemorate the death of Jelinek. He said, the beauty of Fred's approach was simply that it reduced the speech recognition problem to one of producing two statistical models. No intuition or introspection into the human mind was required, just real speech data to train the models. Eventually, his view of the problem entirely reshaped the landscape and set the foundations for virtually all modern speech recognition systems. When you do deep learning in NLP today, you just need real speech data to train the models to some extent. You don't need to know anything about the human mind. So it seems that this perspective kind of won the game. Maybe not entirely true, but quite true, I would say. So the question can be stated like this. If you have machines which reach human performances or are not too far from them in processing language with statistical approaches, should we conclude that we human beings, we also process language statistically? That's a very good question. And as I told you, it's a question that comes with deep learning. Or maybe we process language the way we are, the way we do, and we are very good at it. And machines, they process language in a quite different way, and they also become very good at it. And I mean, why not? It may still be possible. We don't know yet for sure right now. But I wanted to emphasize that. If you are a linguist, you will ask yourself, is NLP just an engineer's thing? If yes, what does it say about language being a very human-specific thing? What is the role of linguistic knowledge? And how can I incorporate linguistic knowledge into a statistical framework? That's not very easy to do, actually. But there are some researchers who work exactly on that. How can we make better statistical models with some injection of some linguistic knowledge? So if you're a linguist, there are still good chances that you might be able to contribute, although the field is dominated by engineers. That's just the way things are. I want to tell you of yet something else that I think is quite important. It is what we call the Turing test. I'm not sure you have heard of it. It was designed by Alan Turing, who is widely known as the father of today's computer science, and back in the 1950s. And it's a test, the Turing test, to assess the intelligence of a machine. And the idea is that you have this test, and if a machine passes the Turing test, it shows an intelligent behavior which is similar or at least undistinguishable to that of a human being. Have you heard of this Turing test before? Is it something you are familiar with? When you study computer science, I guess this is something you come across, but maybe not everybody knows about this one. I'm going to explain it, so don't worry. Okay. Janvier, Olivia, okay. So let me explain how it works. You are subject number C, okay? The one at the bottom of the image. And then you are interacting, you are conversing with A and B. B is another human being, and A is a machine which is designed to produce responses which mimic those of a human. So the machine tries to sound, to look human. And you are C, and you know something. You know that you are in front of both a human being and a machine. And you can interact with both of them with text. You don't see them, You don't hear speech, but you can type stuff on your computer and you receive answers. Now, let's say that after, let's say 1 hour, you don't know who is who. You don't know if B is the human being or if A is the human being, and vice versa for the computer. If you don't know, if you are unable to guess correctly, then you will say that the machine, computer A, passes the Turing test. So that's a very, very famous test in computer science, let's say. I hope that makes sense. So what is interesting here is that the evaluation of how smart the machine is, to some extent, it rests on the ability to produce what? To produce language. To produce linguistic outputs, which are human-like. So what is nice with that is that the Turing test is about creating a machine that will process and generate language in a human way, which means that natural language processing, in a way, questions the nature of human intelligence. So I would say that makes it quite interesting. That raises many questions, this test. What about animals who are also very smart, like bonobos or chimpanzees or gorillas or yet other animals, dolphins, who do not talk? How do we assess their intelligence? Is the Turing test the best test available to assess the intelligence of a machine? Should it go through language? There are many interesting questions lying here, but that's not the key topic of our seminar together. But I want to mention it as a starting point. So you keep these broad ideas in mind and they make you think more and more. So that was my broad introduction with cognitive aspects on computational linguistics and natural language processing. Now, I would like to tell you a little bit more about deep learning and why it plays a role in NLP. So if you know deep learning, that is going to sound quite obvious, the coming slides. Let's see. What I guess you know, I mean, that's quite obvious. Yeah, I think for all of you, deep learning is a subfield of machine learning. And we can very briefly introduce machine learning. You check online, machine learning is the scientific study of algorithms and statistical models that computer systems use to perform a specific task without using explicit instructions, relying on patterns and inference instead. It is seen as a subset of artificial intelligence. Actually, this is what we call weak AI. That's when you try to solve problems effectively with a machine. And that's different from what you may call strong AI. That's when you try to replicate human intelligence. Machine learning, most people using machine learning, they don't try to replicate human intelligence. They just try to address a problem. So algorithms, statistical models, and the idea is that you don't provide rules. You rely on patterns and inference instead. Another definition, the craft of having computers make decisions without providing explicit instructions, thereby allowing the computers to pattern match complex situations and predict what will happen. So if you are practitioners of data science and of machine learning, I think you will agree with me that it's both a science, but it's also a craft. It's a trial and error thing, right? It's something you become better at with time. You need to try. It's not that the recipes are always complete. When you are facing a task, there are different approaches you might take. If some of you are doing statistics, like slightly more advanced statistics, like mixed models, mixed linear regression, or mixed generalized linear regression, you will know, I guess, that it's really hard to know what is the good model that you should adopt for your data. There are all kinds of problems. What should be my structure of random effects? How should I select the right interactions and fixed effects, and so on and so on. So it's a craft in addition to being a science. I think it's important to keep this in mind, because often people, they believe data science is something like, or statistics is about yes or no, is about true or false. But if you practice, you will know the reality is subtler than that, right? So that's machine learning. We can do different things. We can try to cluster inputs according to their features. That's when we don't have predefined categories. I have a research project with some friends, and we work on bonobo communication, the ape, and we try to cluster bonobo calls according to their acoustic features. That's clustering. Also, you have classification. That's when you know the categories beforehand. Maybe you want to classify images of handwritten digits into 10 categories, 0, 1, 2, 3, up to 9. That's what I told you when you try to automatically analyze the postal codes on letters, land mail. Or you might try to learn the relationship between a number of predictors and the predicted variable. And that's what we call regression, of course. For instance, since it's very difficult to store electricity, you want to better understand the relationship between electricity consumption, let's say in a large city or in a country, and the large range of climatic or social parameters, so that you can anticipate consumption. You know that next week in Kigali, the weather will become a little bit become very hot and hotter than usual. And then there will be also this or that event. Then maybe you know that people will turn AC, if they have AC, of course, a little bit more, or people will do this or that, and that will modify the consumption of electricity. And then you can anticipate this. That's when a regression might come in handy. And you might do that with some variables, some numbers, some factors, some categories like male, female, or very good, good, average, bad, very bad, or maybe text, or maybe images, or maybe videos. When you are using machine learning, you could play with all these different things. If we do NLP, of course, we are going to play with text in particular, but also speech recordings. 3 main tasks of machine learning: cluster, classify, regression. That I'm sure you know. Some techniques, they are called non-supervised. Some techniques are called supervised learning. Usually clustering, you can do it with an unsupervised / non-supervised approach. You don't need any supervision. You provide the input data, you apply the algorithm, and you don't need the output data for any kind of training process. Then, of course, you have supervised learning, and then the system will rest on learning the mapping between input data and output data. And the more you have, usually the better. There is a third method, right? I guess you know that there is a third method. Can anyone give this one to me? You have supervised, you have unsupervised learning. Is there a third method that you know of to train a system?
Reinforcement.
Very good.
method.
Yeah. Reinforcement learning is yet something else, right? And the machine is kind of discovering by itself, by playing something a number of times. And you can have, of course, a deep reinforcement learning and all kind of things. So there are actually three methods. But reinforcement is very good, it's very interesting, maybe not as well known as supervised and unsupervised, just to mention it briefly. If you do machine learning, you know, supervised learning, you have a training phase, you have a testing phase. Training phase, you provide the system with the inputs and the corresponding outputs, and you adapt the parameters of the system so that it learns the mapping. And then you want to see how well it performs. That means you have the testing phase. And you compare the outputs of the model for some inputs to the actual outputs. And you see whether there is a good match or not. And then you know about the performance. Very standard approach. What can we do? We can have something like a confusion matrix if we do classification. Or if we do regression, we will try to measure some kind of distance between the predictions and the actual outputs. Very standard stuff in supervised learning, right? We have problems like if we train the system too much with the training set. If we train the system too much, then you have what we call overfitting. The system starts to learn meaningless details and noise rather than general rules. So it overlearns, it learns too much. And as a consequence, it doesn't generalize well. And then you get poor performances in the testing phase. So usually when you train in supervised learning, you need to have enough training, but not too much training. So you need to find how much training is necessary and sufficient or enough. If you play with these kind of things, you know a number of techniques, I'm sure, to address this issue of overfitting and generalization. Standard stuff in machine learning, right? Then you have deep learning. There's a subfield of machine learning, and it falls into the so-called connectionist approaches. This is not something new. In the 80s, people were already experimenting rather with what we know as artificial neural networks, ANN for short. But for a long time, we didn't know how to create very large neural networks, very deep. There were a number of technical problems, mathematical issues. But then at the beginning of the 21st century, some mathematicians, some computer scientists, they had a number of breakthroughs. They changed a number of things. And then learning started to become way, way better. And then you know the current state of things, right? Deep learning, tremendous achievements, revolutionary approach in especially computer vision and NLP. So several long-standing challenges have been solved by deep learning systems, and the performances have increased like in an amazing manner. So that today computer vision is not far from human vision. So it's really, really dramatic. If you have done a bit of deep learning, it's about artificial neurons. These neurons, they are much simpler than the real neurons in our brains. If you want to study the human brain, you will have models with neurons which are way more complicated. Neurons which are described by differential equations and potentials, and you have chemical sides and electrical sides and everything, more like in the real brain. But in artificial neural networks, a neuron is very simple. You have a number of inputs, X1, X2, X3, and so on and so on. And then you have one output. But for each input, the connection has a weight, W1, W2, W3, and so on and so on. Very, very commonly, you take all the inputs, you compute a weighted sum, given the weights of the connections. Then you apply some sort of threshold unit, and that gives you the value of the output. So each neuron takes a number of inputs, produces an output, and then this output is the input for another, or rather other neurons. And that's how you connect the neurons with each other. So you can create architectures. And very, very commonly, you have layers of neurons, and you connect the layers and their neurons together. You can see on the right, you have one input layer, then one hidden layer, and then one output layer. This is what we call the multi-layer perceptron, except that here you only have one hidden layer. So that we cannot call a deep neural network. That's a shallow, in a way, neural network. How does it work? We have all these weights, W1, W2, etc., etc., etc. Initially, we kind of randomize these values. We don't actually randomize them like the simplest method. We have all kinds of initialization patterns, methods, And that's how the networks can learn better. That was one of the challenges that was solved 20 years ago. So what it means training for an artificial neural network is to provide inputs and outputs, and then gradually set the weights of the many connections so that when you provide the inputs, you get the corresponding outputs. So it's supervised learning, and we have all kinds of techniques, most famous one being known as the gradient descent backpropagation algorithm, so that you can gradually modify the weights. We don't really need to enter into details here, and I suspect some of you know this in way more details. What is very important is that the neural network can learn rules, but these rules, they are not explicit, they are implicit, because the rules are kind of distributed in the many weights of the network. So if you have all these numbers, all these values for the connections, as a human being, you cannot infer the rules. They are not explicit at all. You don't see them directly. It's what we call a sub-symbolic system. You don't have symbols, you don't have anything. And then you don't know how the network works. It can perform very well, but you don't know how it performs so well. That's one of the main issues with deep learning. So deep learning means you have many, many layers. That means input layer, output layer, and many intermediate layers in between. In some systems today, you can have up to thousands of layers. Of course, then you need very powerful computers and or a lot of time to train the system. The more layers, maybe the better, at least when you have a lot of data. But at the same time, if you want to learn a lot, if you want to have great learning capacities, you want more neurons, you want more layers. But to train everything, then you need more and more training examples and more training. So there is a cost to very large neural networks. So if you want to succeed at deep learning, you need the right data sets with the inputs and outputs to train the network. But it's also building the right kind of architecture to get the best results. And on the right side, okay, I'm going to answer your question, John. Very good question. You can see on the right side different architectures. And there are actually different mechanisms that go with these different architectures. When you do computer vision, very well known, convolutional layers. Then you have recurrent layers when you deal especially with language. I'll come back to that later on. Today, the best models for language processing, language models, they have what we call attention mechanisms. And then you have fancier approaches like generative adversarial networks and so on and so on. So you have different architectures, you have different mechanisms, and it's a trial and error approach. If you are very experienced, you will have a feeling for things, but it's not like an exact science. You need to experiment quite a lot. And that's a very, very hot research topic. So to come back to John's question, how many neurons shall we use? It depends. For instance, it depends on the size of your inputs, and it depends on the size of your outputs. So actually for the inputs and the output layers, actually is not that difficult when you know what you can feed the network with and what is the output you want. But for the size of the intermediate layers and how many layers do you need, there is no right and wrong answers. There are no right and wrong answers. Different values, different numbers of neurons and layers, they will provide rather similar results, but you still need to be able to find these acceptable values. So if you do machine learning, maybe you know what we call hyperparameter tuning, which means that when you have a machine learning system, we have a number of hyperparameters which define the system itself. So for instance, in a deep neural network, the weights of the connections, these are not hyperparameters. These are the parameters of the model. But when the number of layers, the number of neurons, these are hyperparameters. Either you try different values and you try to find something that works well enough, or actually you can do hyperparameter tuning. And that's very time consuming, but that's a way you can really improve the performances of your model. If you know about other methods like support vector machines, or if you know of methods such as like extreme gradient boosting, you also have hyperparameters, and you can tune them so that the system will give you the best performances given your data set. So it's a tricky question. It's interesting to address this question. It's not so easy, and you need time, because if you need to train so many neural networks, it takes time. But you can do it. Like when I work with bonobo calls, I do that. I do hyperparameter tuning of some neural networks. And there are some, yeah, we are getting there, let's say. But it's still quite recent, I would say. Does that answer your question, John? Okay, I don't see you typing.
Yes, my question was already answered.
Okay.
Thanks.
Okay, good. All right. So if you have played with this convolutional network and autoencoder and GAN and etc., there are many options here, way more than we can cover. What is really nice is that before, when they were building systems, for instance, for computer vision, they would need to extract some features first of the images they were playing with. And that was not very easy. So for instance, let's say you want to process some pictures, and the first thing you would need to do is to apply some edge detectors. And there are some techniques to do that with some simple matrices, and you multiply matrices forever, and then you extract the edges of the objects in your picture. And then that would be a first step to move to a later stage of the processing and gradually extract the content of your picture. But what is so interesting with deep neural network is that when you have more and more hidden layers, you don't need to do that. You don't need to do what we call feature engineering. You let the system by itself extract the abstract features which are relevant for the task at hand. Jean Bosco, the difference between parameters and hyperparameters is that it's a difference of level, okay? So let's say that when you are doing a support vector machine, you will need to set a number of parameters to learn your data. But you can do this with a super vector machine which uses, let's say, a linear kernel or a radius-based kernel. So you have different strategies, and these strategies, they correspond to one hyperparameter with, let's say, two possible values. Or let's say that your kernel is a polynomial, and you can choose how many degrees you want in your polynomial. So hyperparameters are kind of higher level in a way. But for even if you choose, I mean, when you pick up values for the hyperparameters, whatever these values, the system, the way the system will learn will always be the same. You will do it by setting the parameters. So the parameters are set. Okay, that's better like this. The parameters are set automatically during the training process, but the hyperparameters in a way are higher level, and usually you set them yourself, unless you do this automatic hyperparameter tuning, but this is at a higher level. So the weights of the many connections in the neural network, these are parameters. The number of layers, the number of neurons, these are hyperparameters. Different levels in the description of the learning system, in a way. You set them differently, different methods to do that. when you have deep neural networks, like in computer vision, let's say that you provide them with faces of people, like what you can see on this slide, then you want to identify what is the person on the picture. And let's say that you have 4 or 5 different options. The system will learn to extract the meaningful parts of the picture. And that's what is so nice. Then you don't need to spend your time doing feature engineering. As long as you provide enough examples, it will work. That's the beauty of it. That's why deep learning is kind of changing the game. So if you know statistics, if you know linear regression, you will know that in linear regression, let's say that you have a number of predictors, let's say around 5 or 6, your model will have maybe, it depends on the predictors actually, but let's say you will have 10 or 20 or 30 parameters. And 40 parameters is already quite a lot. You need some data to tune these parameters, to set them correctly. But if you consider a deep neural network, you don't have like 30 or 40 parameters. You have millions of parameters, possibly. Or in some models today, you have billions of parameters. So what you can feel intuitively is that when you have so many parameters, it's hard to train the network because there are so many values to set. But then the learning power is huge. The learning is not constrained at all because you don't have a very strict, rigid backbone mathematical equation like what you have in linear regression, for instance. You have all these parameters. They are not easy to set, but if you have enough training samples to train the network, then you may learn very, very complex relationships between inputs and outputs, and then you can make predictions later on. So that's the benefits. But the cost is you need a very, very large training set. The more parameters, the larger the training set. So this is, I've told you, that's why some models only Google or Microsoft or Facebook or a few other companies can train them. And that's why they have this decisive advantage in the race. The other issue is that most deep learning models, they are kind of black boxes. So you don't understand how the network itself understands. That's an issue, of course, right? This is what I've told you before. It's sub-symbolic artificial intelligence. When you have linear regression models, they are way simpler. And then you understand way more what you're doing. But with deep neural networks is another thing. Florence, you are writing like when splitting the data. So I'm not sure what is your question. Of course, when you train the system, usually, yeah, you will split the data between a training set and a testing set, or maybe even better, a training set, a validation set, and a testing set. That's when you do that can be useful for a number of reasons, especially hyperparameter tuning, actually. Today, you also have a field which is growing quickly, which we call explainable AI or XAI. And these are attempts to better understand how black box models achieve their results. What is the recommended percentage for test and train? I would say first, it depends how much data you have. But very commonly, people, they choose 80-20 or 2/3, 1/3, something like this, I would say. But I mean, there is no right answer here, right? But usually, yes, 2/3, 3/4, 80% for the trainings part and less for the testing. And if you need more examples for the training because you have a large system, then maybe you provide more for the training and a little bit less for the testing. But then, of course, your testing will also be more imprecise, right? So there is no right answer here. It's a trade-off. All right. I think maybe you have heard of that. Gender or racial biases in data analysis. So today we have commercial technologies to do facial recognition. Microsoft, IBM, McAfee, they all have their commercial system. And it has been found some years ago already that these systems, they perform better on faces of white men. So if you are a woman, or if you are Black, or if you're Asian, and if you combine being female and being Asian or African or Aboriginal Australian, etc., the system won't perform so well with your face. And that's, of course, an issue. And it was shown that African Americans, they were more likely to be misidentified by such systems used by the police in the US. That's an ethical issue. Why is that? It's because of the supervised learning. It has nothing to do with deep learning itself. It has to do with the biases in the training sets. So if your training set has more faces of males and white people, and especially of white males, don't be surprised if the system performs better on faces of white men, because that's just the result of the training process. So that's a very nice example to show the need for more diversity and inclusiveness in many, many data sets, actually, but also among the digital workers who prepare these data sets and work in these companies. If you have a company where the data sets contain more faces of white males, and most of the people working there are white males themselves, then it's maybe not surprising that they didn't detect that there was this bias. Whereas an African Asian lady could have spotted it. So there are these ethical issues here, which are quite interesting, of course. And there is work to be done. This is yet another very current example, right? You want to analyze X-ray chest scans to diagnose COVID-19. And you provide other information like demographic and clinical data, patient's age and sex, exposure history, symptoms, laboratory tests. You encode all of this, plus the images. You feed this into a neural network, deep neural network, and then you try to predict whether the person has COVID or not, or what is the probability. Typical example of applied computer vision in medicine today with deep learning. The question is, can you do better than a trained radiologist? If not, not so interesting. If as good or better, then of course things become interesting, right? You can try and you can see, when do radiologists and the trained system agree that either someone is positive or negative? And the radiologist could tell you, oh, I know that this person is positive because of this part on the scan. And the machine with a bit of, let's say, explainable AI will also tell you which part of the image was helpful in detecting COVID-19 positivity. That would be here. So here, actually, the radiologists disagree, said no, COVID, and the machine said COVID. Here, they both agreed. And you can see the radiologist said, oh, this is revealing, and this is revealing. But the machine said, oh, actually, yes, this is revealing, but all of this was revealing to me. So you can try to analyze, try to understand how the machine understands itself. So by comparing the performances between the human experts and the machines, then you can try to understand how your algorithm works, where it fails, where it works good, and you can try to improve your system, of course. So this is a typical example of what you may do with a computer vision system. All right. What I'm going to do, I'm not going to do the final part right now. Okay, I'm going to keep it for tomorrow or in a couple of, or in some days, because I would like you to try some activities and to discuss a little bit. in the remaining 50 minutes. Okay, so don't worry, you can have a look at that, but I will tell you a little bit more about this later on. Actually, I will cover everything later on, more or less. So don't worry, I just want to skip it now. I'll come back to it. But what we can do now, let's take 5 minutes again for a short break. And then I have some activities I would like to share with you so that you can brainstorm a little bit and then you can train, you can try a few things. Does that sound good? Shall we take a break, 5 minutes? And then we have some activities until noon, 6 p.m. here. And then that will be good for today. All right. Janvier is okay. If you don't tell me anything, I'm going to assume you are okay with that. All right. So
We are
5
okay,
minutes.
we are okay.
Okay, good. 5 minutes, and then I share a few more things with you. So see you very soon. I'll quickly go to toilets on my side. So we start at 5:15, 11:15 for you.
Bana ubwo wasanga we yaraguze na ntuza na petit frere washaka kumuha igishoro, ubwo urumva uwo ntabwo wamugenderaho. Sawa.
All right. So I hope you are still here with me. I have to conclude the session today. I just have some activities, some questions for you. We can try to brainstorm a little bit. I have some few things just to share with you, stuff you may try. And of course, is related to what I have told you during the last 2 hours. So I've told you about speaker recognition. If you remember, I've told you there are a number of subtasks here. Identify speaker in a closed set of speakers, verify speaker's identity, detect the change of speaker, etc., 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 etc. Now, maybe we don't take 15 minutes because it may be a bit too long. But I would like you to think of the various contexts in which speaker recognition might be used and how it could be, how it could take place. Okay, so if you can try to think maybe for 2-3 minutes, try to think of some cases of possible application, and then what would be the corresponding challenges for the recognition system. So try to think of different contexts with when these techniques could be of interest, where you could design a system that would be useful for the people and for the company, let's say. And what could be the challenges? How could that work? Okay. So I'm going to show you this. I'm going to do it like this. I'm going to show you this in the chat so that you have this in the chat. Everybody can see it. And then I'm just going to show you this one again. So I'm giving you, let's say 3 minutes, 3-4 minutes. Just try to think of how this could be useful, in which context, which situation. And then you can share with me, share with everybody actually, either by typing in the chat or by turning on your mic. So maybe just think of it for, let's say 3-4 minutes. Try to think of something. Okay, so who would like to propose something? Maybe in an investigation where the visuals were not captured, but the audio of suspects. Okay. Okay, I like this one. So that's the context of like the legal context, right? Or the judiciary context. You would have some suspects and you would have the audio recording of these suspects. You would have recordings of someone doing something bad. And then you have suspects, and then you would like to know which of them, who among them did the bad thing, right? Let's say, broadly speaking. So what would be the challenges of something like that? If we just spend some time on this one first. I would say, for instance, that let's say we captured the voices of the subjects by having some software on their phones, something like that. And we could turn on the phone without them knowing it. Then maybe the quality of the recording is not very nice. And then the verification, for instance, or the identification will be harder than in a case where you speak in front of a very high quality microphone, and here the performances would very likely be higher. Also, if you have captured something, you have no control about what was captured, which is different from other situations. So you hope that you have enough for the system to come up with something, or with some probabilities of who was speaking at first. So that's an interesting case. Okay, in a quarrel situation, when there is a need to identify someone who insults someone else, I think, yeah, that's another option for sure. That's not so far maybe from the first one. And we have the same kind of limitations, I would say. And that's different maybe at the gate for security purpose before allowing visitors and households of compounds. So that's another thing that could work, okay? You could do it with a retinal scan. Maybe you could do it, let's say, let's imagine with fingerprints. That's more maybe, I'm not sure, but yeah, you could also have identification through voice. Here, what is the difference? What is a possible difference with the previous situation? What could you do when you are at the gate like this? That would be different from when you have recordings of suspects. Of course, as Celestin noticed, if you have people who have similar voices, who sound similar, of course, that makes it more difficult for the system, right? Okay, so indeed, if you have, the content of what was said in the first place, maybe the words could be different, maybe the kind of sounds that were produced could be different, that could be a problem. But something that you can do at the security gate that you cannot do in the other context is the system asks you to produce a sentence, then tries to identify you. But if it doesn't succeed with what it has, it can tell you, oh, could you try again? And then you could do it with another sentence, which is not possible when you have recording of suspects, let's say on the phone. So that's one difference. If people are recorded unknowingly, they are unlikely to fake their voice, maybe. But in front of a closed door, maybe you could have someone trying to fake the identity of someone else, trying to sound like him or her to get the door open. So you see different situations, slightly different challenges. In medicine, when testing a given disease that affects the voice, okay, I think I get it. So using speaker recognition or some features of the speaker's voice to see when the voice maybe is damaged or affected by some disease. Yeah, I think we could think of something like that. The context would be quite different. Okay, Agnes, very good. In focus group discussion, So that's an interview technique in group in social psychology, very well known by companies when they want, for instance, to know what people think of a new product. You invite people and you conduct a focus group discussion, and you have everybody speaking in turns. And you would like a system to differentiate the participants, and maybe with automatic transcription or something like that. Yeah, that would be very interesting as well. Here, likely you wouldn't have people trying to fake their voices, right? But if they kind of overlap with each other, if one interrupts another one and you have one voice over the other, I can tell you that this is very tricky. But if they don't, if they let each other speak, then that could be an interesting case. So that's another good option. Yeah. So these are good examples. Do we have a final thing? Okay, Yvette, it can be used in market research when the recorders and cameras are used in supermarket to identify customer satisfaction, customer wishes. Yeah, so we could imagine that. I think that makes sense. A system where the person would interact with the machine and his or her voice would be recorded. And let's say that we could try to analyze emotions in the voice. So some properties, does the speaker belong to the class of happy customers, or the class are rather unhappy customers after their experience in the market, or in the shop, or in the supermarket, or wherever? Yeah, I think that, why not? Okay. Any question? Any comment on this? Or can you guess? Can you see the number of situations that we could consider here? I think your examples are quite diverse. So
And
faking,
also,
yeah, please go.
And also, yeah, I think, like, suppose maybe security is at home, you want to be accessing like the home, like open the door maybe by voice recognition. So maybe you are sick that day, you have a cough, and then you are out, and then you end up like you're back, you want to go in, and then the voice has completely changed. So you may be denied access to your own home.
Very good.
That's the only way in.
I like this one. Okay. Then you can imagine two things here, I would say. Maybe you have a system, but you also have a key. So the system is just so that you don't need to take the key out of your pocket. So if it doesn't work, you're good. You can still enter your home. But let's say indeed that your voice is affected, and then the system does not recognize you anymore. That's kind of a problem, right? But let's imagine now that when you were discussing with your friend going home, someone in your back, knowing that you have such a system, recorded your voice. Then it's quite easy for this person to enter, right? So it depends on the level of security we want, right? If we want high level of security, then the number of solutions are not really okay. Olivia is also mentioning chatbots. So indeed, when you have interactions with chatbots, you could perhaps try to identify a number of features, try to follow in case there would be several people speaking at the same time. There could be also, we could perhaps use some of the techniques behind these different tasks to make the interaction with the chatbot like richer and more satisfying for the user. That's good. Okay, very good. All good answers. Okay, you can think more of it, and you would find that there are quite a large number of situations. And if you can come with something very, very innovative, that's how some people eventually they may create startups and sell a new product, right? Using these techniques. All right. I want to share something else with you, which is quite fun, quite interesting. Diane, so we can change the audio into test so that the analysis is easy. I'm not sure exactly what you mean. For sure, you could have a system trained with a number of people. And then, of course, when it's working in a kind of a post-training phase so that things are more fine-tuned and the performances are better. But what we know today is that these systems, it's not like fingerprints, okay? The level of recognition is not to the level of what you can get with fingerprints. And it's too easy to fake voices. So that makes these systems based on voice not so robust as soon as faking, trying to cheat the system is something that could happen. Yeah, so that's how I understand maybe what you wrote, Jan, but I'm not entirely sure. What you see on this page is a book that was published quite some time ago. I don't know if you can read the year, but that's several decades ago. I think I can try to find it. I think maybe it's written on the next slide. It's in the 70s or something like that, or maybe even 60s. And as you can see, what is written on the front page of this book, the cover of this book, it was the first book ever written by a computer. So you had two programmers, Chamberlain and Ether, and they spent quite some time writing a program. So of course, it's not deep learning or anything. It's based on rules. It's an old classical approach to text generation. But they wrote this program, and then they let the program generate text. And they made a compilation of these things. And you can find them in this book. And the software was named Ractor. And the title of the book was generated by Ractor itself. And that was a weird title, but anyway, the policeman's beard is half constructed. So when you read this book, and actually I could upload it to the Google Drive if you want to have a further look, it's quite interesting, it's kind of bizarre. So I created this small assignment for you. On the next slide, I'm going to show you 4 poems. And it turns out that it's a kind of Turing test, okay? Kind of. 2 of the 4 poems you are going to see have been written by actual poets. And the 2 others were written by this computer program I've just mentioned. So I would like to look at these 4 poems, and I would like you to find which ones are human and which ones are not. And I would like to know what are your arguments to decide that one is human or one is generated by a computer. So that's your task. So these are the 4 poems. I'm going to give you 2 minutes to have a look at them. And then you can tell me which one do you think are human and which ones you think are non-human. Some poems, actually, you might know them because they are well-known poems. So if you know them, that would be easier. But if you don't know, try your best. So I'll give you 2 minutes to read them and then try to make your choice.
Hello, Professor.
Yes?
Yeah, would you repeat the question? Because on my side it was like a bit breaking.
You want me to repeat the question, right?
Yes, sir.
Oh, sure. Okay. You can see 4 poems on this slide, okay? 2 were written by human poets and 2 were written by a machine. Can you find which one is which one? Which ones are made by a machine? Which ones are made by humans? So you can, let's say we call the first one, let's say we call them like,
iyo dokima y'imbere umuntu witwa Gatete mu kigo reba aho ofisi ya iri umurebemo uramubaza. All right.
so can you try either by turning on your mic or by typing? Do you think 1 is machine, 2 is machine, 3, 4? So Chantal, 1 would be would have been written by a machine. You can tell me why you think it's like this. 2 is human, okay. Do you agree with Chantal, or do you have other opinions about the 1 and 2? And why do you say that? How do you know the second one is human and the first one comes from a machine? If you know because you knew the poems before, then don't mention that, okay? So does anyone have any idea? How can you distinguish? What about 3? What about 4? Okay, Chantal, okay. The first poem is kind of words combined together, but no emotional display or something like that. Okay, I think that makes sense. So what about number 3 then? Would you say it's by a machine or by a human being? Number 3. Okay, 3 by a machine. And what would be the reason for 3? Is it the same because of the emotional display that is kind of absent? Anyone else? Or you just find it's a difficult task? Do you agree it's not so easy?
It is a bit complex, sir.
Okay, of course.
Because like,
yeah,
yeah,
on,
because like, because like when you see almost like the characters to read it to verify whether it is written by a person or machine, and you know that that person is almost using by typing in machine, not written on like a paper. So where that's when we can recognize that this is really written by a human.
Sure, yes. Of course, I don't give you this kind of information to make it more difficult. And of course, this is a specific case, right? This is a case of poetry. Poetry to that, I mean, this is a specific type of writing, and that makes it, of course, more confusing. So, shall I give you the answer? Yeah.
Before you hand over the answer, so really exactly, if we want to verify really it is written by a person, because you know that that person will be just using a machine already automatically. So again, also another thing, again,
Somewhat, sorry, I missed the final word because the communication kind of dropped. Can you repeat the last part?
No, the logic which is behind. So to recognize that this is written by a machine or by a human.
I don't have any, actually, I don't have any arguments to provide you with, actually. I think it makes sense to try to see indeed, you could, I mean, the first thing you could check is whether the sentences, they are kind of grammatically correct, right? But here, because we are dealing with a special kind of poetry and not like something like a news article, the grammar is kind of not messed up, but is kind of free, right? Words are kind of flowing in a slightly different way. So I'm not sure they are very good, actually, indicators. I like the idea that was proposed by Chantal of emotional display. Maybe that's something like this, but still, I would say is not so easy. So I don't really have much to suggest. I just want you to feel that it is not so easy. That's just my point, actually. So maybe I show you the answer. You had some time to try it. So actually the first one, Night Sky and Fields of Black, this is by Rachter. The second one, the Earth. Oh, okay, you can't see the answer. So because I hid the answer. Yeah, you can see the answer here. The second one is actually a very famous French poem and poet, is Paul Éluard. And the Earth is blue like an orange. So this one, French people from France, maybe some people, they would have recognized it. Maybe some of you recognize it, actually. You could well have known it before. But in the French version, La Terre est bleue comme une orange, this one is from, I mean, he was famous at that time, at least. Maybe now it's kind of gone already. But this one is from someone. Then the third one is from a very famous writer, Lewis Carroll, and that's called The First Riddle. And then the last one is also, once again, is The Machine. But how can you know easily? Definitely, there is no easy way to know. It's just that in some circumstances, people will write in a way that machines maybe can imitate rather well. It depends on the situation. But if it's about some sort of contemporary poetry, quite free in terms of structure, stuff like that, it's difficult to guess. So that's what I wanted to emphasize. I want to show you something that is at the end of the lecture, but I haven't shown you yet. I want to introduce briefly a conversational agent named Mina. Mina is a system that was created recently, like 1 or 2 years ago, and it's just is something to interact with. You can chat with this Mina, and Mina has like really good performances when it comes to a chatbot. And it was trained with a huge amount of conversation from public social media posts. So it's 341 gigabytes of data for the training. And this is a language model with 2.6 billion parameters. And that was trained by people working at Google. And the performances are really nice. So you have an example on the right. Hi, how are you this fine evening? I'm doing well. It's morning my time. Then Mina will change. Good morning. What are your plans for today? Get my work done, then watch a movie at home in the night. Sounds fun. What movie? So you see, she picked up movie and then she's asking, I haven't decided yet, perhaps an Oscar nominated one. Any suggestion? And then the program answers, I'm not too familiar with recent Oscar winners, but I do know I wanted to see the Grand Budapest Hotel. Tell me about that movie. Then some explanation. I've searched on the internet and both movies are very colorful. I'm looking forward to it. I love colorful movies. I think you will agree with me that this interaction sounds rather natural, right? It's pretty good. It's not like the machine answers something very, very stupid and, let's say, totally out of place. So that's the kind of stuff Mina can do, and that's the state of the art, more or less, a conversational agent today. This is two other examples. The first one is quite good. Human says, Says you are in an empty giant office and you see a blackbird flying indoors. What do? And then Mina will ask some question. What kind of bird? Is it friendly? Yeah.
Sorry, Professor.
Yeah.
Hello, Professor.
Yes, I hear you.
Sorry. Sorry to interrupt you. I'm begging because I was almost out of the network. So would you give me back to the answers?
Like this one. I'm just basically, if I repeat, I'm introducing a
the other
software.
poems, the other poetry from 1 up to 4, where it was differentiating if it is a human or the
This
machine.
one, I don't think they try to do the Turing test, but it's just, I mean, they just had people interact with it, and then they recorded some nice examples of conversation with the software, so that you can see how well it does. But I mean, you could try to play the Turing test with this system, but here the conversation I report, they are not part of an experiment where you would try to do that. I'm not aware of that, at least. So it's just some examples of conversation. Like if you would try to interact with it, that could be the kind of conversation that could take place. So I've given you one, and then I was just giving you another one. Mina will ask some question. Is it friendly? How large? How big is the office? Is it indoors or outdoors? And then human says, well, it's a predator bird and it's gonna eat you. And then Mina, it still remembers the first question, and then it answers. I would grab my phone and call 911, which I think is pretty reasonable, right? So that's what Mina would produce. And then you have a third conversation where actually it is making a kind of joke. Actually, it's maybe not so easy to get when you are not a native speaker of English, but it can even in some circumstances make some kind of jokes. So what I want to tell you here is that today the performances are becoming really good. It's difficult to train such a system like this, but once it's trained, then you can use it, which is the nice part, of course. I'm not sure it's available to download right now. So you could use it on your computer, or I guess it's not free, but I haven't checked recently. I should do that. So I'm not sure you can interact with it for free online. But what I want to show you is that we have made a lot of progress. There is a program very well known that was released in 1966 by someone named Weizenbaum. He was a pioneer in artificial intelligence. And he created one of the very, very first chatbots or chatterbots. So the name of this program is ELIZA. And the idea is that this chatbot is working sort of like a psychotherapist. And it does a kind of psychotherapy that we call Rogerian. That's after the name of a famous psychotherapist. And basically the way the conversation goes is that the program asks you questions and try to make you do some sort of introspection or something like that. You are going to try the program to finish the session. But what I want to tell you before you try is that some people, they talk to it, like back in the 1960s, 1970s, and some people, not knowing it was a machine, some people actually believed for a while that it was a real psychotherapist. So actually, I would like you to try this one. If you check the address on the web, on my slide, I'm going to copy it here. If you go there, you can actually interact with a version of ELIZA. So I would suggest you go online and you give it a try for a couple of minutes. Just give it a try and then let me know what you think. That's one of the very, very first chatbot. 1966 is a very long time ago today. Of course, it's not as good as what we can do today, but just have a look because this is very, very famous. The first chatbot. and then you tell me what you feel. So please take a few minutes to do that. And you can type in the chat if you want. And I will try myself at the same time. Is it working for everybody? Can you all access it and play with it? Should be okay. I guess there should be no problem for you to give it a try.
Yes, actually we are trying it.
Very good. I typed something just so that you could see, but if you are all trying something, then you are experiencing it by yourself.
Sorry to interrupt you. What the purpose of it?
I mean, is a kind of demonstration, actually. At that time, it was, I mean, in the 60s, that was some interesting software. Today is way too simple. But at that time, it was demonstrating how a computer might pick up some words and might try to initiate some sort of discussion with a human user. So that's a chatbot, but like without any specific commercial application or anything. So Chantal, you say, yeah, Elisa is not very accurate in responding. Do you agree with that? Okay. No, it's not very accurate, or no, it's not true that it's not very accurate. Janvier.
Okay. So yeah, I think response time, it's actually good, but then it doesn't really get the conversation so well that you can rely on it that much.
Okay. Yeah, I think that's a fair statement. Okay, that's a fair statement. Let's continue. How have you been? How have you been? How is your day? What about your own day? Mine is great, and yours? Tell me more about that. Typical Eliza. The program will always try to kind of escape, right, and try to return the focus on you. That's one thing. We're discussing you, not me. Why are you weird? Would you prefer if I weren't weird? I do. That's quite interesting. All right. Okay. So the way it works is that it tries to pick up some words in what you write, and then there are a number of possible frames. And the idea is to insert your word into the frame and come back to you very often with a question. So that's why the response time is is low. I mean, is fast, because actually for today's computers power, this is nothing. I mean, there's not like 3 billion parameters like for Mina. But then, of course, the results is not very, very impressive. But let's say that you come with some psychological issues, and then you are told you are going to interact through the internet with a psychotherapist. Then you might get confused for a little while. And it seems that back in the days, some people, they did not notice that much. Just because they were into the conversation and they were discussing something that mattered to them, and they didn't know it was a computer, And if you would ask them after 5 minutes, how is it going? How is it going? They would say, well, it's okay. It's a psychotherapist. And they would kind of get tricked. It's not the Turing test, because the Turing test, you know there is a machine and you know there is a real human being. But in a context like this, you could feel for a little while that it's a real human being that is interacting with you. So I hope you find this like intriguing. It's not accurate, it's not very convincing. But remember, that's something that was made more than 50 years ago. And it's not good, but it's not that bad. If you would try to write the program yourself, I mean, you could do it definitely, but it would take some time, and it would take some careful thinking. Of course, if you compare with Mina, then the situation is very, very different. So I want to show you the progress that have been made, basically. I hope that makes sense. I want to show you this. Okay, so the ELISA effect. So we call it the ELISA effect. Actually, there is that it gave its name to this psychological effect, which is our propensity to see the behavior of a computer as more human than it actually is in an appropriate context. Yeah, it's not that bad, I would say. Is the same, I would say. I mean, is the idea that we project human behaviors and human abilities on robots, but also on animals. You may feel that your cat or your dog understands very well what you're telling him or her. Maybe there is some ELISA effect in that. So that's kind of similar. And maybe it's an effect which can be taken advantage of for good reasons, or maybe also for bad reasons. If you've heard that in countries like Japan, they experiment with robots to take care of elderly people because the population is quite old on average and they don't have the manpower to do that. They will have robots to help elderly people, and actually the elderly people, they will interact with the robots and they will attribute them more abilities than they actually have. But actually it's good in that case, because then they will feel less alone and better taken care of, something like that. I want to show you this weird video. Imagine two Mina, not as good as Mina, but something in between Mina and ELISA. And you have these two bots and you put them in front of each other and you let them discuss. And then you can hear what you get.
I know, you are a clever machine.
I am a human sitting in front of a machine using it.
Why are you lying to me?
I am not lying.
You are lying about being a bot.
Well, you are unpredictable.
I prefer to be unpredictable. It keeps things fresh.
But how do you manage to stay unpredictable?
Because you said it.
No, I didn't.
Yes, you did. Stop lying.
And it goes on like
I'm
this
not lying.
for minutes and minutes and minutes. And you see that they call themselves Vladimir and Estragon, but sometimes they will also use different names. And they have this very weird out of space conversation together. Of course, there is no business application for having two computers exchange like this, but you can see how it goes. You can see whether it feels super weird or not. And then you can, of course, interact as a human being with one of these bots. Okay, so maybe that's more about creation, creative approaches, things like that. That can also be part of NLP. It's kind of fun. You will observe something weird being generated. But of course, most of the time, you want to create a bot like this, like Alexa, the stuff sold by Amazon, which can do a number of things which are required by users. So I'm not sure if you have heard of this Alexa, whether it's a thing that you can find in a place like Rwanda. But I mean, these are things that people can buy and have at home. And then they can ask, can you tell me what will the weather be like tomorrow? And then the machine will answer. Or can you play this song by that musical band? And the machine will find it and it will play the music, the song, and so on and so on. So these are just illustrations of what you can do with conversational agents. If you want later on, you can try these ones. These are two that you can find online and you can give it a try. And there are yet others. They are not state of the art, but they are more recent attempts to create these chatbots. So this is part of NLP. And you can try and you can see what you feel about them, whether you are convinced or not. And this is what I wanted to share with you before ending the session. Okay, as a more introductory side. Okay, so it's a 6 p.m. So that means for you, it should be noon and everybody should start to get hungry. So I hope you found it relevant and interesting what we've covered today. That was more introductory, that was more general. Tomorrow we will start to consider something more specific. Okay, let me see if we do speech recognition or spell checking. I will maybe change the order, but tomorrow we will look a little bit more at the techniques. We will start to investigate more in details. But today I wanted to show you NLP, like paint a broader picture. Okay, if you have any question right now, please ask, no problem. Otherwise, if you need to go because it's noon, please feel free to go. And then thank you for joining. And of course, I will wait for you tomorrow, 9 a.m. for you. And then we'll move on, right? So that will be our second session together. So once again, I hope you found it interesting, and I can stay a little bit if you have any question you would like to ask. No problem, my pleasure. Yes, so hopefully everything has been recorded apart from the very beginning. So it will be processed and then I will receive an email. And what I can do, I'm going to create like maybe a Word file and I will put it on Google Drive. And then I will give you the link to the recordings so you can access them. We can do like this. Okay. So then see you tomorrow morning for you. Yeah. Have a good day.
You too. Thank you.
Thank you.
See you.
Bye-bye. If you have any question, please do not hesitate. I'm happy to try to answer anything.